Okay, let's do an example where we don't get zero for the electric force on some charged particle. So let's place it in a way that we can still get some intuition, but the force is not zero. So here's our x-axis, and we don't really need the negative x part, but let me just draw part of it. What we want to do is to place two charged particles, let's say of charge q star, at, so this one is also a particle of charge q star. They are at, this one's at x equals a, and this one's at y equals a. And so, and we'll place a particle, let's see, maybe for simplicity, we'll place a particle over here of charge q naught, and these are all positively charged particles, and we want to show that because the force on this one due to this one is to the right, and the force on this one due to this one is upwards, and these two have the same magnitude, we'll get a net force which is at 45 degrees with respect to the horizontal. So we should get some net force that way. So we'll have components x and y that are the same. We want to show that. So let's first write the electric field. It's the sum of the electric fields of each particle. So that looks like k q star times x minus a. This is the generic electric field produced by this particle, plus y minus 0 j hat over the usual horizontal component squared plus the vertical component squared to the 3/2. And to that we'll add the electric field produced by this particle everywhere in the xy plane, and that is x minus the x component, so that's just x. I actually don't need the parentheses there, plus y minus a there because the y component is a, and we'll divide that by x squared plus y minus a squared to the 3/2. Now the force at any location in the xy plane on the particle of charge q naught is, of course, k q star q naught times x minus a I hat plus y j hat. I'm basically rewriting the whole thing. The first term and the second term has k q star q naught times x I hat plus y minus a j hat over x squared plus y minus a squared to the 3/2. And we want to evaluate this at x equals a, y equals a, and that gives us a force which is k q star q naught times, since x is a, this term disappears, and y is equal to a, so we have a j hat here over x is 0, x is a, so this whole thing is 0, and y is a, so we get a squared to the 3/2, we get a cubed here, plus k q star q naught times x is equal to a, and y is equal to a, so this term disappears. So we just get a I hat here over a squared plus 0 to the 3 halves. So we get an a squared cube, just like we get over there. So let's just get rid of this. Okay, so indeed we have two components, and this reduces to, right, we have 1 over a squared, so this one becomes k q star. Let's just pull out the k q star q naught over a squared, which is common to both terms. And then we have what's left in here is j hat, and what's left here is I hat. And therefore we have indeed a force which is pointing equally in the x and y direction.